My name is Ting Zhang. In this section, I'm going to talk about plausible values. So when you conduct any PIAC analysis, focus on proficiency or skills, you have to use plausible values. This section, I'm going to explain what are plausible values, why we have to use plausible values, and how to use them in your data analysis. All right, first of all, let's look at the plausible values. Whenever you open a PIAC data file, you will find that under each domain, for example, the literacy domain, instead of 1 scores for each individual, you'll find that each individual actually have 10 scores. So from the manual and the documentation, we learned that the plausible values are the proficiency estimate for individual, drawn at random from a conditional distribution of potential scale scores. And when you do the analysis, all available plausible values should be used when calculating summary statistics for a group of students. But why we have to do that? All right, let's dive into it. All right, so why we have to use plausible values? It all has to do with assessment designs. So the PIAC used a special design that the respondents only took a subset of the test questions from the item pool. However, at the assessment level, all items are measured. So let's see how PIAC cycle 2 works. So each respondent, first of all, took a background question there. After that, they complete locator items in literacy or numeracy. So depend on their performance, they are routed to either a foundational components or different level of literacy or numeracy blocks. So after that, many of the respondents are also assigned adaptive problem-solving block randomly. So this block is independent of the adaptive routing, meaning it's not dependent on the respondent performance on the locator items. All right, so why we have to use this assessment design that respondents only took a small set of the items? Okay, let's talk about it. So it definitely have certain advantages. It's cost efficient because the item pool usually have hundreds of items. So just giving them a small portion of the items can avoid overburning those respondents. But at the assessment level, it achieves a broader coverage of the targeted content domain. And PX cycle 2 better measure lower or higher level scales. Of course, it had trade-offs. Because each respondent receives too few test questions, their scale scores has a lot of measurement errors. So if we just use the scale score we got from the test items, they were administrated. We are very likely to make inaccurate inferences because of measurement error or because of uncertainties, the scale score we got from a small portion of the items. Then what do we do? All right. So PIAC and also other large-scale assessment like PISA, TEAMS, and the US NAEP assessment, they usually treat the missing scores, treating the items that didn't administrate to the respondent, treated those items as missing data. So the student proficiency or their responses on those unadministered items actually are imputed. So students or respondents' proficiencies actually are imputed based on all the data available, including their responses, item responses on the limited test items they took, and also all the responses to the background questionnaires. So from the imputation, we actually can get a student proficiency distribution. Look like this. And it represents uncertainty of the student skills. See, it has a variance. So in order to capture this variance called imputation variance or measurement error, we randomly draw, for PIAC, randomly draw 10 scores from this distribution. And those scores are called plausible values. Why we have to use the plausible values? Because with all the plausible values, it actually captures the variance and the measurement error or uncertainties associated with the estimation we have for the student scale. All right, let's talk about how PIAC score are generated. It took 4 stages. I'm going to dive into each stage in the next few slides so you understand actually how it works. All right, so at the first stage, item response theory models fit into the respondent item responses. So PIAC use the 2 logistic item response model for dichotomous items, and use a generalized partial credit model for the polytomous items. So through the IRT models, we got 2 outcomes. First of all is item parameters from those items. Second is the participants' likelihood functions for their proficiency. All right, so usually for the standard test, that in the test, each respondent took all the items. We end here. Just 1 score from the IRT model, usually the EPA will be treated as a student final score. However, for the PIAC, we cannot do that. Why? Because each respondent only took a small number of items. There are so many uncertainties associated with their scores. So we need to do something to adjust the uncertainty to obtain more information to adjust the uncertainty about their proficiency. That's why in the second stage, we fit into a latent regression model to their background information. So this model is called population model. So let's look at the model equation. So theta sub I is a latent distribution that represents the proficiency of the student on the domains we measure. So the X sub I are the observed respondents to the background question items. So remember, PIAC collect a huge number of background information from each respondent, like their, for example, workforce, their education background, and some demographic information. So in operation, when we feed a latent regression model to their background data, we don't really use the raw data. What we did is we conduct a principal component analysis first to reduce the dimension of X to a manageable number. So eventually we use the principal components as a predictors in the latent regression. So from this model, what we really want to get is a theta sub I, which is a distribution, also represent student or respondents' proficiency in a domain. At the third stage, we combine two models together. Remember, at the first stage, we feed in a IRT model. We got a likelihood function from this IRT model. At the second stage, we feed in a latent regression. Well, we also got another proficiency distribution theta I from it. So we combined the two models together to get the final model here. And this is the model we got the final posterior distribution. So let me show you using figures, help you better understand how it works. All right. So at the first stage, again, the green part, we're feeding IRT model here. So from the model, we got the likelihood distribution of student proficiency. As I said, there are so much uncertainties about this distribution. So we need to adjust it. We need to get more information to adjust this distribution. So from this model, the latent regression model, we got a second distribution, which is in a Bayesian context, is a prior for that model. So the combination of the two distribution is a final posterior distribution that the plausible values are based on. So we draw plausible values, 10 plausible values from this final distribution. All right, so again, just an illustration, how we do that from the posterior distribution from the third stage. So we have 10 scores, 10 plausible values for each domain. How do we analyze it? Because this is actually a multiple imputation model. We will use the Rubin's multiple imputation method to calculate the measurement errors. All right, so let me show you how to do that. All right, so this is Rubin's imputation method. Let T be the population parameter of the interest. For example, the mean scores of literacy, and M be the number of plausible values. In our case, in PIAC case, M equals to 10. So we use each plausible value to get a mean to evaluate the T, and do this for 10 times for each plausible values. So the final estimate, the final mean that we want to get is the average across all the 10 plausible values. So that's how we got the final estimate such as mean. All right, so whenever we do analysis, we also have to use a standard errors. Let's look into how we calculate the standard error. In other words, variance. All right. When we do an analysis, the variance in plausible value estimates actually has two parts. The first part is a measurement error we talked about, captured by all 10 plausible values. Another error is from the sampling. Um, so Paul already talked about it. So sampling also has sampling errors. So we have to combine the two parts together. So the first part, again, is between imputation variance. In other words, the measurement error. So this is a formula to calculate the measurement error. And we also have to do sampling. We have to calculate sampling variance. And here's a formula for the sampling variance. So for PIAC, we use JK2 or BR estimates to do that. One caveat we should pay attention is the sampling variance actually has to be computed for each plausible values, and the final sampling variance is average of the variance across all plausible values. Then at the final stage, we combine the measurement error, the imputation variance, with the sampling variance. Here's a variance we have to use in our plausible value analysis. And notice the measurement error or the imputation variance actually being adjusted using this term. And the red part is a sampling variance. All right, so why does it matter? Why we have to use all the plausible values? Why we have to take into account the measurement errors into our analysis? Let me show you an example. So in this example, I ran two analyses using a survey. So in the first example, I want to look at the mean difference, the gender difference in terms of literacy achievement. So the outcome is a literacy mean. Instead of using all the plausible values, I just use the first plausible values, PV, LIT1. And this is outcome from that survey. So in the second analysis, I ask a survey to use all the plausible values in this analysis. And then the results is presented here. So I do want you to look at the means and the standard errors of means across these two examples. And you will see the means are slightly different across each level between these two examples, right? And if you compare the standard errors, you will find that the standard error, if we use the first plausible values, they are lower than the corresponding standard errors from the second example. So we can draw different conclusions if we don't use all the plausible value in our analysis. So that's a takeaway I want you to pay attention. All right, conclusions. So when we conduct PIAC analysis to obtain a valid PIAC estimates, we need to take into consideration of the PIAC complex survey sampling design and their complex assessment designs. So what does that mean? That means in your analysis, you always want to apply appropriate weights in your analysis, and all the plausible values need to be used for your analysis to capture the correct variance for your analysis. All right, it's complicated, right? When you think about all the formulas, you have to follow the Rubin's rules. But don't worry, the statistical package at Survey actually incorporated uh, all the method into its analysis. So in the next session, Paul and I are going to show you how to use at Survey and how at Survey took the sampling error and the measurement error into consideration in their analysis. All right, here are some further considerations you can rate. Now let's move to the ad survey session.